We use Bluewaters to advance a key simulation technology that is primarily used to build and test virtual prototypes, so complex engineering products. We aim to increase the practical impact of large-scale engineering simulations performed by using implicit finite element method. I would like to briefly introduce the collaborators. Dr. Said Courage is the PI of the project. Dr. Robert Lucas is the co-PI. The project has a diverse research team, members from different stakeholders in HPC. Rolls-Royce and Cray are partners of the industry program at NCSA. I'm a staff member in NCSA's industry program. We help private sector companies to address their HPC challenges, and LSTC is a close collaborator as well. I'll continue with a brief overview of the project. Today, virtual prototypes or digital twins are used to augment, supplement physical tests in engineering, design, and certification processes. The vision is to move to a fully virtual digital product development process, which will require a long-term continuous improvement effort to achieve. The immediate goal is to increase the current impact of simulations. And the current practical impact is tightly coupled to the performance scaling of the simulation code. As an HPC project, the focus here is on performance scaling. The simulation code is a general-purpose finite element code, LS-DYNA, and the engineering product of focus is jet engines. Rolls-Royce provided representative real-life models having as many as 200 million degrees of freedom. The overall approach is to push everything in terms of scale and improve. Before moving to more technical details, I would like to expand a bit on the challenges and constraints. The top group applies more specifically to major engineering codes like LS-DYNA, and the bottom group is more universal. One of the prime constraints is the legacy nature of the code we have in hand. We just cannot start from scratch to design the code. Another important challenge is that key algorithms in the code are NP complete, meaning they are inefficient by their nature. And under the title of more universal challenges, one can highlight portability, performance trade-offs, and increasing complexity of hardware. This is the status at the beginning of the Bluewaters project. The prime metric is execution time, and scaling behavior is tightly coupled to the overall impact. The jet engine model in consideration as 100 million degrees of freedom and run for 3 implicit time steps. Execution time plotted versus total number of MPI ranks, and each rank has 8 threads. Speeds up well till around 500 ranks. The right half of the plot is generally an exotic space in terms of scale for engineering codes. We can see that initially how things were inefficient above the 500 rank level. Here's the how the improvement framework looks like. The goal is to carry the computational workflow from terascale towards petascale. And in plain terms, we stress the workflow, break it, and improve. We have a large workflow in hand, and there are many moving pieces under the hood in different sections of the workflow. Serial, pure MPI, and hybrid programming models are used. Aside from existing priorities and associated trade-offs, previously unknown bottlenecks required ad hoc design decisions. The overall effort included a spectrum of work from small modifications to developing entirely new algorithms. In all those improvement stages, we have leveraged NCSA's OVIS tool. OVIS provided us a large collection of system-level data collected at runtime. OVIS visualizations were critical for our understanding of the behavior of the workflow, and this is a representative memory profile of a master node. Next, I would like to provide more details about the workflow. We have a large and sparse linear system resulting from finite element equations. And we use a direct multi-frontal method to solve it. The sub-steps can be classified as input processing, matrix reordering to reduce the so-called fill-in, symbolic factorization, numeric factorization, and triangular solutions. In plain terms, we factor because the triangular systems are easier to solve. The main feature of the multi-frontal method is that factorization is performed through partial factorizations of small and dense submatrices called fronts, and those fronts are handled by fast blast operations. The sequence of operations is guided by an assembly tree obtained with the help of a graph partitioner. What's special about the assembly tree is that operations on the leaf nodes can be performed independently, which provides a natural parallelization strategy. Factorization is historically most studied part of the workflow. Here we are building on decades of prior art. It dominates the numerical complexity, factorization, but it's not the main scaling problem. As seen on the right-hand side plot, both the memory footprint, the blue curve, and the flop rate of factorization, the orange curve, scales up to 16,000 threads for a problem size of 100 million degrees of freedom. Okay, here we are doing some due diligence. We have benchmarked the project's direct solver MF2 against MUMPS. MUMPS is one of the gold standard direct solvers in the field. Direct solvers are generally the default choice in single physics as well as segregated and fully coupled multi-physics schemes. Primarily for their robustness in handling ill-conditioned problems. So as we see in both pure MPI and hybrid modes, MF2 is competitive with the state-of-the-art alternative. LS-TC team developed a new scalable nested dissection reordering algorithm. So this part of the workflow was a sequential bottleneck at the beginning of the project. The initial serial algorithm, METIS, failed to run our hero problem with 200 million degrees of freedom. Okay. Reordering is NP complete and needs a heuristic algorithm. Meaning there is no proof that the algorithm always is fast, and produces good results. Row operations performed to eliminate non-zero elements in locations. In initial locations might have created new non-zero elements in other locations as a side effect, the so-called fill-in phenomenon. And the quality of reordering directly affects the factorization memory footprint and flop rate. The figure shows a reordering quality comparison. Number of non-zeros normalized with respect to METIS values. No code wins all the time. So all of the relatively modern nested dissection algorithms are competitive. Okay, together with the ordering quality, what matters as well is parallel scaling, along with LSG part, Prometheus, and PD Scotch or other well-known parallel reordering algorithms. PD Scotch ordering quality falls off with processor count, and LSG part is competitive with Prometheus for large processor counts, what it was primarily designed for. Next, I would like to show scaling results for the new symbolic factorization. Symbolic factorization is an analysis step before the actual numeric factorization. It determines the non-zero structures of factors and initiates data structures. Results show that symbolic factorization of domains, the middle red bands, is dramatically reduced, and separators, 10 colored band above, is increasing as expected. But at the blue water scale, around 40% of time is spent parsing the input, which requires rethinking. This is a before and after comparison. Execution time plotted versus total number of MPI ranks. The blue curve is what we had at the beginning. The orange curve is where we are now with pure MPI. And the bottommost gray curve is the current scaling achieved with hybrid parallelization during the life of this project. We see scaling up to 2,000 ranks. Actually, it's better than it looks. Here, time is distorted by long input processing time. In real workloads, there are thousands of load steps, not 3. So for a more representative production run, deltas in time will become more pronounced. To put things into a more general perspective, here's the overall impact on the time to solution for our grand challenge problem with 200 million degrees of freedom. Hours to solution plotted in the log scale. So we see an impressive reduction from 7 weeks to overnight as a result of more resources and new simulation technology introduced during this project. And I'll leave you with a few concluding remarks. Here we barely scratched the surface. Industrial challenges are well beyond the capabilities of today's hardware and software. The special collaboration model we have and access to blue waters were crucial to the success of the project. And I would like to extend our special thanks to Blue Waters SaaS team for great technical support. Thank you.